How are you guys doing? What's going on? Uh-oh. You guys stressed out? You got final or midterms? Is
Yeah,
that what's going on?
I have to read two novels.
All right, all right. That's
Days.
good. This is the only time in your life where all you will have to do is read novels, so that's good. You will have to cram that in on the way to work next time. Um, what else? What's going on? Anything interesting? Any problems with the assignments? Anything like that? Everybody's all right. I got a few emails with people's videos. So that's good. Keep doing that. If you're missing videos, don't fail this class. There's no reason you can't get an A in this class. You just have to do the work. All right. What else? What else? What else? Um, what's going on with you guys in the back? You guys are having a great old time back there. What's going on? No? All right. Sadly, it seems like we are coming to the end of the sun. I think this will be the last day we talk entirely about the sun. We're gonna move on to other stars after this, so that's fun. Uh, all right. Well,
Stars we know even less about.
yeah, stars we can see even less light from. Even though we have a hard time with the light from the most bright object in the sky, you can't even look at it. It's so bright, which is just mind-bending if you think about it. All right, so just like every class, what is the central tension at the heart of astrophysics and cosmology? Somebody in the back, please tell me. I'm going to keep picking on. I'm going to actually start calling your names soon to tell me this. So you can, if you don't know it, listen up because someone's going to say it, and I'm going to ask you to say it next time. So, what's the central tension at the heart of cosmology and astrophysics today? What is at the crux of the biscuit, as they say in rock climbing? Anybody? Back row? For yes.
Are you looking for something that we have specifically talked about?
Yeah. Since the first day, pretty much. Why are we talking about the sun so much? Who cares about the sun? Emmeline.
Gravity?
Not quite. Gravity is not, well, gravity is poorly misunderstood, but it's not at the central tension of astrophysics. My friends, in back. Come on. Mario? What's up with the sun? What's crazy about the sun? Yeah.
Well, we spent a great deal of time talking about how the sun produces energy and fission.
Fusion.
Fusion. So
Yep.
is that what you're looking
Yeah. So we're going to talk about fusion today, finally. Um, so you're kind of working backwards from the why. What is the what, though? Okay, Abby.
Whether the sun is a gas or a liquid.
Yeah, that's it. So all you guys in the back, write that down. Write it on your foreheads. What's that?
I was just say, you probably should write it down right now.
Yeah, write it on your hand.
Every
Yeah.
time.
I'm going to just start calling your names next time. Whether the sun is a gas or a liquid. Whether the stars are a gas or a liquid. Why does it matter? It matters, we can start with how the sun powers itself because the way that we power things on Earth, in some sense, is chasing the dream of how the sun powers stuff. There might be some problems with that, so that's not even my favorite reason. Why else does it matter? Who cares if the sun's a liquid or a gas? Yeah, Brandon.
Will help us understand the other stars that are in the universe and other galaxies and reframe how we think about them.
Yeah, I think that's a huge piece of it. And then kind of the meta level final reason why this matters at all. Maybe this is a little more subtle, but why does it matter for kind of everything in science? Go ahead.
Because everything else, the more abstract theories, all are based currently in astrophysics, at least in cosmology, are based on the assumption that the sun is a gas.
How do you think that affects like the rest of science, though?
So, well,
It's kind of meta. This is kind of meta. I don't know if you guys have picked up on this yet. It's okay. What do you think? Anybody? Who cares? Why does it matter if we, why does it matter that we fix how we think about the stars and the cosmos in terms of how it's going to impact the rest of science, maybe other things on Earth beyond science even? Kevin, yeah.
Can help us solve our issues with nuclear fusion and solve our
Other than fusion, other than fusion. I know. That's okay. Yeah.
It very fundamentally affects our idea, our theoretical framework of how, well, just stars in general, but also the theories you're using to explain how the stars behave, like how.
What about beyond the stars, though? Who cares? How would us changing our mind about the stars matter for the rest of science? Yeah.
Because
You're right, though.
there's it's more of a like a human mental thing,
Okay.
basically.
I like that. Keep going.
That currently science is built off of the idea of failure.
Yeah.
Of a theory that's being created, and then new evidence comes about, new observations prove that theory wrong, and a new theory supersedes it.
Yeah.
Currently, we're in a sort of the wall we've hit
Yeah.
with science is this refusal from people in the field to relinquish a theory that could be so obviously incorrect.
Yeah.
And so breakthroughs in all, it's basically just a reframing of how we think about science.
Does that make sense to you guys? I think you're right about that, Dante, in big broad strokes. Does that make sense to anybody back there? No. I see. That's okay. Thanks for saying no. I appreciate that. All right. Here's the thing. What the heck is science, right? Science is supposed to be this story, this system of telling stories about the natural world that we iterate on. So we examine all the possible reasons. Why is there light coming from the ceiling right now? Is it just a bunch of fairies that live in the light bulbs that are doing it? Maybe. Let's rule out that possibility. Let's go look and see if there's fairies inside the light bulbs, right? So science is really cool, ideally, because it allows us to exclude really bad ideas, right? Now, it can't ever tell us for certain what the right idea is, but if it's working properly as a tool, it allows us to rule out bad ideas. Why does it matter that we have a tool that allows us to rule out bad ideas? In the back. Cares. Who cares if we can rule out bad ideas? And who cares if we can do it objectively? Yeah, go ahead.
Well, I think, at least to me, ruling out bad ideas is it's just the standards. But like to rule out a bad idea is just you do that. You don't want to be doing the wrong thing. You don't want to be going off incorrect information.
Yeah, well, that's really bad too if an entire civilization is going off bad information, right? Because I don't know if you guys noticed, but every civilization that ever existed is gone now, right? That's a pretty rough precedent for our civilization to wake up into, right? Usually the reason they're gone is because they acted upon narratives, upon stories about reality that were broken in some way. And they proceeded as if it wasn't a big deal, and it usually fell apart. Yeah.
I think a big fundamental of science seems to be to not blindly believe everything you're taught and told and to question.
Yeah. And why is it bad to blindly believe?
If you aren't able to critically think for yourself.
Yeah, critically think, right? So I would offer to you guys that the only reason that we're able to sit here in this classroom with nice temperature controlled environments and whatever the heck you guys are going to eat for dinner will be nice and warm and on the table is because we are really good at thinking. And that's really what humans do. That's special. And what is thinking exactly? What is it? What does it mean to think? Yeah, in the back.
Process, sense your just inputs.
Yeah. Well, thinking is maybe not just as simple as processing sensory inputs, right? Because I think a lot of animals do, even little bacteria do a lot of sensory input processing. But what is weird about thinking? There's something special humans have. Yeah.
We're able to synthesize something new from what we learned.
Bingo. Right?
I want to add to that.
Go for it.
We're also able to extrapolate and expand from what is literal and right and is obvious and in front of us to the abstract. Abstraction is one of the key things that marks high intelligence in a species and humans. Even it's when I was remember I was saying one of my favorite examples is that we found spheres from 300,000, 400,000 years ago. They were not just the branches of trees; they were the very cores of huge spruce trees because they were the hardest part of the tree, the best wood, and they shaped them so that, like modern javelins, they're better for being thrown because their weight is heavier toward the tip. That is an abstraction of an idea. It's simple. The goal is simple, but it's abstracting it from something much that it's a simple idea that's abstracted into a much larger one.
Yeah, and what's crazy is that in order to build that spear, people had to tell other people what they were doing, and they had to put those ideas they'd encode them in language and pass them along to other people. So if you go and look at like other primates, they actually can use tools. Like they develop some cool videos on YouTube you can check out of these, I think they're chimps who are digging around in these ant holes with sticks and stuff. The difference is they're not iterating on the design of that stick, and there's not people watching over their shoulder picking up ideas. Hey, I used the core of this tree because it works a lot better. I can get deeper into this hole. They're not communicating those abstractions the same way. The other part you mentioned was this kind of projection into the future, and this is what I want to talk about. This is kind of the core of what humans do. I think of us kind of as time machines, actually. We have this unique ability to examine the past, even though it's not here. You can literally close your eyes and think about something in the past. You can likewise close your eyes and think about something in the future that hasn't happened here. You can take yourself to a different place. You can put yourself in a different person's head. You can go somewhere deep into the future or deep into the past. This is insane. This is absolutely amazing. This is our fundamental talent as a species. One second, Kevin. The thing that I want to point out to you is that science is a really cool tool for being able to tell stories that you can get from one person's head into another, and evaluating whether that story makes sense objectively or not. Fairies giving us light from the ceiling. Well, we can go and look and see if that's true. We can also reason from first principles whether that's a consistent story. Well, how did the fairies do what they were doing? I don't know. Well, then it's not science, right? If it's missing any pieces of the story, then it's not living up to our standard, right? It has to be consistent internally. So the beauty of a civilization like ours having a science that's consistent, that means no parts of it contradict each other, is that it's a reliable story. And if we have reliable stories and we're a civilization that values reliable stories, then the future looks a lot brighter than otherwise. Because if you're a civilization that has unreliable, inconsistent stories, then basically whoever gets the biggest microphone or has the most money or has the biggest castle or the most tanks gets to do and say whatever they want about the future, right? And that's a really scary situation, and it's played out a number of times on our planet, probably much more times than the alternative. This is the first moment in history where we've all had a way of evaluating what's happening objectively, discussing it, getting it into each other's heads, and then deciding as an entire human race, essentially, what we want the future to look like. So, when it comes back to this question I asked at the beginning, who cares if astronomy and astrophysics and cosmology make sense? How does it possibly matter for the rest of the world? Well, it matters because if we're telling a story that's in any way completely invalidated or internally inconsistent, then we're on a bad road towards a world where things don't have to make sense anymore. And that's freaking scary, honestly. If you look at different civilizations where things didn't have to make sense, it doesn't work out for those people, right? And even in recent history, even if you think about, places like Stalinist USSR, you think about Maoist China, you think about places where millions of people starved to death and lost their lives. Those were civilizations where the leader says whatever they want and it doesn't have to make sense, and that's a really, really scary situation. The beauty of this country, in some sense, the promise of it, is that we can all pay attention to what's happening. We can all follow what's happening, ideally. That's the idea of a free press, anyways. And we can make decisions. That's the only way a democracy even works, is if we can all see and understand what's happening and then make decisions based on it, right? So again, I go back to the beginning. Who cares if cosmology and astrophysics isn't internally consistent? The answer is everybody, even people who don't care about the stars, should care whether some sort of science is internally consistent or not. It's kind of scary otherwise. Do you guys have thoughts?
I just had a small comment that one of the first steps to authoritarianism is anti-intellectualism.
Yeah, absolutely. I mean, and that's a little bit of a complicated situation, right? So there's a lot of doubt in the past years, particularly since the COVID era, in expertise. There's a lot of pushback and radicalism against intellectuals. This is true. The problem is some of the intellectuals don't make it easy on the opposition to that movement, right? Because if you're sitting there at the top of some intellectual pyramid insisting that, A does not equal A, that your story doesn't have to be consistent, that there's fairies in the light bulb, and I don't have to explain how they're doing the magic, that's a problem. That really makes it look bad for the rest of us who are absolutely committed to objective explanations for natural phenomena, right? So the problem sometimes can come from within, not always from without. I mean, you don't want to give the barbarians ammunition, right? So,
No, I was just gonna say, we also have the ability to kind of fabricate other worlds and tell lessons and stories that way as well.
yeah, it's the beauty of the human imagination. I think that's why well, I'm not going to get into AI right now, but humans can do something special that computers will never be able to do. And you guys should pay attention to that, because the computers are going to take all the other jobs. But if you focus on that one thing that humans do that nobody else can do, which is this whole sort of time machine process I'm talking about, this imagination side of things, then you'll have plenty of work to do. And you will have a very productive and meaningful life. Yeah.
One of the last signs of, like, I guess they're calling it sapiens, basically, this Homo sapiens. One of the key things that humans are able to do that a few other species are able to do, but we only discovered in recent times, is self-reflection and knowing and being able to recognize oneself. One of the easiest tests is a mirror, right? But also when you are able to look in, when it's, an animal is able to look inward upon itself, it's then able to look outward with more clarity. And
Yeah, and we have to be able to do that as a species too, right? We can definitely make, ideally. We can also put ourselves in other people's heads. That's insane. I mean, I would advocate that you'll probably be better at making friends and getting along with people, and maybe even resolving conflicts with the friends that you do have. You'll probably stay married longer and all of these other things if you get really good at putting yourself in other people's heads.
empathy,
Empathy.
that is the definition.
Yeah. Um, So anyways, I think all of these things are playing out in this story that we've been telling. And I think that it's ideally going to be a beautiful renaissance, because it's going to teach us a lot about the process of changing our minds, about the process of bringing something that's inconsistent, a huge apparatus. I mean, the amount of money that is inside of astrophysics and cosmology that has to be brought back into alignment with what's actually a profitable future of discovery is huge. There's a lot of realignment that has to be done. I think this can be a really, really beautiful time for humanity. So if we think about the last time this happened, it was actually really, really cool. So what happened 500 years ago? I don't know if it was 400 or 500 years ago, when we had the Copernican revolution, right? We basically saw the birth of an entirely new revitalization of people trying to figure out how the natural world worked. And it wasn't a disaster, it wasn't an apocalypse, it was just all good. So anyways, I'm gonna ask you guys in the back again. next time what the central crisis is and why it matters. And we're gonna get to the point where you can tell me instead of me telling you. And if we can pull that off, this will have been a success of a class. All right, and you'll do all the work and get your A's, and everybody will be happy and check your boxes and move on and get very high-paying jobs later, or whatever you want. Okay.
My material goals are beyond your understanding.
Well, yeah, you do need that paperwork to get it, to climb the ladders sometimes. All right, where do we go from here? Wait a second. So I think that I am starting far too late in this presentation, but that's okay. We can catch ourselves up. Okay, so last time, what did we talk about? That's why I had the wrong number up, because it was actually the wrong presentation. All right. What did we do last time? We talked about the history of the gaseous sun. Somebody, I know I don't expect you guys to nail all of these points exactly, but there was kind of 5 main pieces that went into the gaseous sun. So everybody thought the sun was a solid or a liquid for almost all of time. And then all of a sudden, in the 1800s, people changed their mind and they turned the sun into a ball of gas. How did that happen? Does anybody remember, in no particular orders, any of the reasons why that happened? Yeah.
Is the first one black body experience?
Yes, absolutely. Do you remember anything about that exactly? Black bodies, she says.
Guy with the heat rotation.
Anybody? Black bodies, black bodies, black bodies. Yeah. Evan.
I remember that we had talked about, I forget the scientist's name.
Kirchhoff.
Kirchhoff, who used these piece of soot in his experiment. And was it him?
Oh, that was Planck, actually, the theorist, the mathematician.
Yes.
Yes, he built on Kirchhoff's wishful dream that any substance could create a black body if it was enclosed, anything that was opaque. What's the problem with that? What's the problem with thinking that any substance can behave as if it is this beautiful black body? Dylan?
Wouldn't the Earth be completely black?
That's a good point too. Yeah, yeah. Reflective cavities wouldn't exist. Mirrors wouldn't exist. There's all sorts of insane consequences of that. Now, Planck kind of realized it because he needed an absorber for his experiment, for his mathematical processing. So he sticks a piece of soot in the middle of his reflective black body, and it all works out. It is true, if you put any kind of a perfect absorber, into a cavity, it will thermalize the radiation. So it will turn it into that black body spectrum eventually. Yeah.
Could you repeat the sentence you just said, please?
I don't remember what it was. Darn it. Sorry, I'm on a roll here. The basic idea is that, the reason that I mentioned that as being a huge piece of the story is because that beautiful rainbow of light that we see from the surface of the sun, the only way to produce it in a laboratory, it's actually quite easy. You basically have to just heat up a solid or a liquid. If you want to get a perfect version of it, you got to use a special kind of solid or liquid, which is perfectly absorbent. It's a black body. It is perfectly black. This makes sense though, guys, right? You ever been out on a sunny day, you're wearing a black t-shirt, it's very hot, right? Because black absorbs all the light, right? You wear a white t-shirt, it reflects a lot of the light. You wear sunscreen, it's like zinc oxide. What is it? It's like white paint. It's just reflecting the sun off of your face or whatever, right? So reflectors and absorbers. Black bodies are perfect absorbers. The surface of the sun is very black. It's very black, actually. That means that it turns heat into light very, very well. Okay, so that was one of the big, big moments. These guys were studying these spectra, and they made a really weird theoretical loop where they just assumed that, hey, maybe any substance can do this. Okay, that was the first step. What else? Anybody remember any other points from the last class? Yeah, please remind me your name again. I'm so sorry. Kansas. Should be easy to remember.
And it said there were phase changes.
Ah, yeah. The phase diagrams. Do you guys?
Pressure caused phase shift.
Yeah. What was the deal with the phase studies back then? What's a phase, by the way? Phases of matter. You guys ever heard that? What's it mean? What's it like? Give me an example. Anything you can think of. Kevin.
It's where something as it gets warmer and more pressurized, it goes from like solid to liquid to gas or to plasma or back and forth, so on.
Yeah, it's kind of a difficult concept to grasp in some sense, but it really involves the way that the atoms are attached to each other ultimately, right? I'm not sure plasma is actually a phase, but we'll deal with that later. So, when you have a gas, the atoms have no interactions with each other. They're literally just bouncing off each other. They don't stick at all. When you have a liquid, they're a little bit sticky. When you have a solid, they're really stuck together. Yeah.
Yeah, phases of. That's why I was knocking on it because this is one form of one phase of matter is this chair, and then this air is another phase of matter.
Yeah. And actually, if you light that table on fire, it'll turn into a gaseous phase in some sense, right? So don't do that.
Don't don't do
Don't light fires.
Don't light fires inside a building. Okay, so what was going on with the phase studies? People were just starting to realize, oh my goodness, if you start squishing stuff, start squishing gases, well, what'll happen? Well, what do we know now, obviously? What do we know now about squishing gases? Particularly hydrogen, because the sun's made out of hydrogen, right? It's our simplest atom. It's mostly hydrogen. What do we know about squishing gases like hydrogen today that they didn't know back then? Yeah. That's right. That's absolutely right. It turns into a liquid. Why didn't they know that back then? In the back, yeah.
They didn't. I assume they didn't have the technology to sufficiently compress.
Yeah. They didn't. Neither had the technology to compress it, nor the ability to read out whether it had actually changed into that form. Yeah.
Part of it was also they didn't have access at least to the types of vacuum chambers that we have now. Because one of the ways that we can are able to compress, at least I know one of the cases I saw was nitrogen from gas into liquid. From just compression, it requires a vacuum to do that, to require the pressures, to have the pressures required for that to happen.
Yeah, I'm embarrassed. I don't know enough about how this actual experiment was done, so that's something I need to read up on more. But yeah, they weren't able to see it though back then. That's kind of the main point here. All right, so they didn't know that if you squished hydrogen, they actually thought, and Andrews wrote this famous article that you could compress hydrogen all day long, as much pressure as they could generate in the lab, and it would never turn into a liquid. So that was two. So any material can make this black spectrum we see off the sun in any material really, in any phase. Kirchhoff really thought that it could apply to gases too if you squished them hard enough. Andrews said, hey, you can't squish hydrogen enough to turn it into a liquid. What else? There's a couple more.
I'm blanking on the name of
That's okay.
but you would put up onto the projector a image of compressed gases. It might have been hydrogen with the spectrograph or something.
Mm-hmm.
Lines were like fuzzy.
Yeah, they're fuzzy. Yeah, that's a good point. I can't. They're two German names, Plucker and Hittorf, I believe. Yeah, so people had discovered this phenomenon called pressure broadening, which is really splitting the lines when you pressurize them. So, you can imagine that the light, we've talked about light in this class, but light's a particular oscillatory phenomenon that atoms do. And as you squish them, they vibrate differently, right? So you can actually spread out these lines, these individual frequencies can spread out a little bit. So knowing that when you pressurize gases, you could spread their frequencies a little bit, maybe you could just have the right amount of spread and you could get that really nice rainbow eventually. That was the hopefulness, yeah.
I also wrote down two others. One was solar system, the theory of solar system formation at the time, the nebular accretion.
Yeah, so people had inherited from one of the great philosophers of the 18th century, 17th and 18th century, several of them actually, Laplace, Kant, amongst others, that this solar system could be explained as having formed out of a swirling nebula of gas, right? So that was a sort of cosmological story that they'd inherited from the previous generations. So that was in play. What was the last one?
And the last one is how the sun powered itself.
That's right. That's right. And that kind of brings us.
Like radioactive decay, fission. There's the idea of like it's just pressurizing itself so much, it's getting energy, and fusion became the only one that was left.
Perfect. So that brings us up to today. So powering the sun, how did it do it? They tried everything, right? These guys were just starting to play with heat engines in the 1800s, right? They were starting to play with all sorts of steam engines and heat engines, and thermodynamics was a new science. And they thought, well, if we could power the sun by squishing it, because we can do that in our engines. And people were okay with that for a while. And then they started crunching the numbers and they realized, oh man, it's gonna run out of fuel in like a few million years. That's not good. And then they started hearing from other scientists that the Earth was really, really old, like millions and millions of years. We now know it's thousands of millions of years, maybe much, 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 much more. But the timelines weren't working out. So they needed to have a new way to power the stars. And that's kind of what we're up to today, because kind of phenomenally, nobody had a way to power the stars for like 50 or 60 years, but they knew that it couldn't be compression. They knew they were looking for something else. Famously, one of the last holdouts with the liquid idea was this British astronomer named James Jeans. And Jeans was holding out that it was some sort of nuclear process, like fission, like radioactive decay, because that was just starting to be studied at the time, right? Do you know what killed Jeans's idea, though? Anybody? They didn't know the sun was made out of hydrogen yet, actually. They just put that together. It was actually this young woman named Cecilia Payne who figured that out from the spectroscopic analysis, that the sun was hydrogen. Hydrogen didn't undergo rapid nuclear decay, and so that wasn't going to work. It wasn't made out of these big, heavy atoms at the bottom of the periodic table like James Jeans had hoped. So Jeans, this really hurt him, and he kind of, stopped fighting for the liquid sun at that point because he had no way to power it. He was kind of one of the last guys. So yeah, it brings us up to the concept of fusion in some sense. I'm going to skip this for now. Come back to that. All right, so there was a little bit of a saga that played out over the beginning of the 20th century, and this concerns this concept of fusion. So let's see if we can't kind of make sense of this. I think at the end of class last time, I introduced Eddington and Einstein. So who are these two guys, Eddington and Einstein? Why? Who is Eddington, first of all? Anybody remember? Yeah.
It's the best one.
That's right. Yeah. It's kind of a popularizer. Yeah, exactly. That's right.
But in the New York Times.
Yeah, he wrote it up in the New York Times too, right? He really made Einstein's work cool. I know it sounds insane, but that is true. Of course, Einstein, the Germans were not popular at this point in time with the West in general, at least the free West over here. So Eddington introduced it. Eddington was also a pretty good mathematician and scientist in his own right. And he was a great lecturer too. This was back in a time when lecturing was the alternative to watching YouTube. So people really made circuits out of lecturing. And one of Eddington's famous lectures, he sort of threw out the idea that maybe there was a way to power the stars with some sort of atomic process that hadn't been discovered yet. So to understand why Eddington said this, by the way, Eddington said that about 20 years, 15, 20 years before fusion had really been worked out as a real mechanism and empirically demonstrated. So if we want to understand how in the world Eddington came to that conclusion before he even knew what it was, we have to understand what Einstein was putting down, because Eddington's tie with Einstein really permitted him to think about it in this new way. So Einstein has this famous E equals mc squared thing, right? You guys have all heard that before, right? All right. We'll see if we can't unpack this a little bit, because this way of thinking is what got Eddington onto the idea that maybe the stars could be powered by something other than being squished. Oops. So, getting ahead of myself. So it starts with this word energy. Energy equals mass times the speed of light squared. Energy. Let's talk about energy. Okay, I think this was sort of the cliffhanger we ended on last time. I said, your textbook claims that Einstein's equation E equals mc squared means that matter can be converted into energy, and energy can be converted into matter. Okay, and I said, I don't know if that's really what that equation means. I think there's a better way of understanding it. And Kevin said, well, what is it? I said, I'll tell you next time. So we're gonna get to it here in a second. All right, but what is energy? Because that's the first step. Let me read you a little quote from your textbook that I found extremely cringe, but I think this is really important, actually. Energy is a challenging concept to grasp because it exists in so many different forms that it defies any simple explanation. In many ways, comprehending energy is like comprehending wealth. There are various forms of wealth, and they follow different rules depending on it, if they're in the stock market, real estate, a collection of old comic books, great piles of cash, or one of many other ways to make and lose money. It's a lot easier to discuss two forms of wealth or energy than to discuss the concept in general. Okay, well, I think, that's funny I say that. I believe that thinking requires us to define these concepts very clearly and carefully. I think it's actually really insane to use words like energy if we don't have a good definition for what that concept is. And I would say that for almost any word in science. Now look, you might get away with it when you're hanging out with your buddies, like, I don't have a lot of energy today, or, yeah, can what, I don't even know what else. You guys use it all the time, right? Can you feel the energy of this room or something, right? Like, it has like some valence in a poetic sense. So that concept can be loose, it can be generalizable, it can apply to lots of situations in everyday language. Science is different though, remember? Because science requires us to tell special kinds of stories that are excruciatingly self-consistent. That means that every single word you use in a scientific theory has to be clearly understood by the person who's reading it. Energy can't just mean whatever the heck I want it to mean, right? Like, oh, the fairies are doing whatever they want in the light bulbs. Don't worry about it. No, that doesn't work for us here. That won't work. So the reason I said that statement's kind of cringe is that they're basically shrugging their shoulders. They're like, it's in equations. Don't worry about it. It's hard to understand, kids. You'll be all right. It's not okay, actually. We have to make sense of this word. So
I love when my book that's supposed to explain scientific concepts to me tells me don't worry about
don't worry about it. It's complicated, kid. No, it's not that complicated, actually. Yeah.
Is that a common talking point that energy can't really be defined?
It is a very common talking point for a lot of physics terms, unfortunately. And this is, I could teach a whole other course about quantum physics and why there's going to be a renaissance in quantum physics as well. But that comes down to completely ill-defined concepts as well. So I think at the beginning of this course, I mentioned, and we're going to keep circling back on it today, that we don't really have a material model for the atom today, right? We have a mathematical atom. So much of physics is like that. We don't actually have material descriptions of what's happening. We certainly don't have material explanations for what's happening, but we do have really powerful equations. So how do you make a really powerful equation without having any idea what's materially happening? It's a good question. Anybody?
Guess and check.
Yeah, that's absolutely right. Yeah. You screw around and find out what happens, and then you write it down, and then you modify your equation, right? It works really, really well. It's called it's basically the scientific method that you were taught in high school, right? You have some sort of, you fit some curve to some data, and then you try to generalize it, and if it doesn't work, then you retool that model. And yeah, you can build really powerful equations. This is basically how we've done everything in this room, from the projector to the Zoom meeting to the camera. I mean, incredible works. Understanding very little about the material representation of what's happening behind the scenes. Yeah.
Or you go against what the scientific method is supposed to be, and because what I've seen is people with math starting with their thesis, getting evidence, doing the experiment, and when the evidence of their experiment goes against their thesis, basically disproves it, they don't change their thesis to reflect what the evidence shows. They change the experiment again to try and fit their thesis again and again, and change the math a little bit to try and fit their thesis because they want their thesis to be true.
That's an unfortunate thing that does play out, and that's certainly playing out the liquid versus gas argument in the sun. Yeah, that's the funny thing about math too, is that it's very difficult to understand for most people. And so you can get away. I love to tell this story. I tell this story all the time, but I think you guys, it's worth hearing. So when you do a PhD, perhaps the scariest moment of the PhD is that when you're basically done, you write this huge book, you have to write a thesis. It's basically like the worst term paper you've ever had to write. It takes you years and years. You have to call together a committee of experts, and you have to go, and they've read your thesis, and you have to stand up in front of the room and defend it. So they just pick on it, right? And they pick on you and ask you questions. And you have to bring someone from an outside institution. So I was at Columbia University in New York. I had to get somebody from another institution. I brought in one of the most famous material scientists in the world at the time, this dude at MIT. He came down on the train from Boston, and he was at my thesis defense, and he's picking on different parts of things. We're going along okay. And then at some point, he gets to a piece of mathematics in my thesis, and he goes, I don't understand what this equation says. And I kind of explain it to him and stuff. And he goes, I still don't understand, but that's okay, right? Which is crazy, because this dude's like a mathematical genius, and my math was like fine, but it wasn't, brilliant or anything. My point is that math is really hard even for experts to compare notes on at the end of the day. People specialize in particular mathematical tools, and they become very comfortable and familiar with them. And at some point, there's only a handful of people in the world who are really able to check each other's notes on certain things. That was a real wake-up moment for me, where I was like, oh, this is crazy. I basically could have written anything I wanted in that mathematical equation, and nobody would have been able to check me on it, which is insane. So math is weird, and you can say things in mathematics, you can make statements that may or may not be reflective of reality, because you can push things far beyond their physical reality would permit otherwise. So anyways, we have a very mathematical physics. A lot of it has been empirically tested in the technological realm, and that's wonderful. But a lot of it hasn't, and we're going to keep seeing where the math butts up with reality in this course. But when it comes to this concept of energy, we've kind of reached this interesting wall where the textbook says, hey, Einstein had this brilliant revelation. Energy is equal to mass times the speed of light squared. I don't really know what energy is. Don't worry about it. It's complicated. We have a bunch of equations for it. Okay. Well, what the heck is this concept of energy? What does it mean inside of science? So let's kind of take this all the way back. So this word that's written up here, does anybody speak Greek? Me neither. But the word is actually Greek. Aristotle was the first person to write this. It's actually just energia, right?
Energia?
Yeah, nothing crazy. It sounds kind of Latin or Spanish in a way. Okay, so now, basically, what did Aristotle mean by it? Any guesses? Why did he use this? So Aristotle basically used it to mean activity in the natural world, some sort of activity, some sort of business going on, all right? So people this was 4th century BC, so what is that? Oh my goodness, that's like 2,500 years ago, long, long time ago. A lot of the things that the Greeks came up with were super far out and ahead of their time, and they got forgotten more or less for the next 1,500 years or something. So when people started to play around with these concepts a bit later, I think last semester we talked more about Newton's different laws of motion and stuff like that. We didn't have time for it this semester. One thing Newton introduced was this concept of momentum. Anybody remember what momentum is? Yeah.
The movement of molecules as a whole rather than the individual atoms themselves.
Yeah, it's really just something in motion, right? So the easiest way to write momentum is let's not do that. Yeah.
Momentum is also the like storage of motion, and so and then the transfer of that from one body to another.
Yeah, it's kind of the first quantity that people realize is conserved across processes, right? So if I have something really big moving at, or it doesn't matter how big it is, something's big or small, whatever, it's moving with a certain speed, then that amount of material in that amount of motion is going to stay the same as long as nothing else comes into the room. And if something else comes into the room and collides with it, then that same quantity of motion is going to be transferred into that new body, right? So this first idea that there's this quantity in nature that's conserved. So, downstream of Newton, a bit later, there's this dude named Leibniz, who's actually quite an interesting, let's see, where was this guy from? Leibniz. I want to say that he was Prussian. Gosh, I could get that wrong. Anyways, sounds like a Prussian name, doesn't it? Oh, it's going to be embarrassing if I get this wrong. Somebody look up where Leibniz is from. This is going to kill me. Anyways, Leibniz had the realization, Leibniz. Leibniz had the realization after thinking about things a little bit, particularly about pendulums and elasticity, that there was another quantity that might be conserved. He realized, was it Saxony? So Germany, yeah. Okay. So he kind of had this interesting idea. He was like, if you drop a ball, right? It has at some certain height, it will reach some speed v, right? It'll get going to some velocity. Well, if you tie that ball to what becomes a pendulum, essentially, not only does it reach a speed v at the bottom, it also has enough speed to get it back up to the top again. So in some sense, you have two velocities there that are contained within this this body in motion, right? And he started thinking about this in terms of collisions in general. When things rebound, they also have velocity that's capable in the backwards direction if I throw a tennis ball against the wall. So the way to mathematically encode this was as v times v, or v squared. There's two of these v's in the equation all of a sudden. And you realize this was a conserved quantity too, kind of like momentum, this mv squared stuff, right? This mv squared thing, he called it vis viva, which really just means like life force in some sense, something like that. Okay, so this idea stuck around for quite a while. And it wasn't really recognized as a truly conserved quantity for many years, many years later. Actually, another lady named Émilie de Châtelet wrote in her copy of Newton's Principia that she believed that this vis viva was actually a fully conserved quantity of nature. She's a really interesting character, actually. Her and Voltaire, just amazing if you want to get into that. Anyways, so people started thinking about this mv squared business as a conserved quantity, much like momentum, which is mv. At some point, the thermodynamicists started thinking about this as well, right? So for thermodynamicists, everything was about forces and pressures and all of this stuff. Well, they realized that this quantity could be essentially this kinetic quantity, this mass and velocity could be redescribed in terms of forces as well. And they used the term work to do it, right? You guys heard that term work? I'm trying not to bore you to death with this mathematics. But basically, the thermodynamicists realized that there was a more generalizable principle that they could use to describe how much work could be done by a system. and that it was proportional to this old vis viva idea, or this energy idea that was starting to come about. And by the end of the 1800s, basically everything had been reconverted from simple force laws and stuff into these really complex energy descriptions. That was the new term that was being used, which is based on the joule, which is a unit of work from the thermodynamicists. So everything in physics was starting to be written in terms of this more generalizable dynamic concept of energy. Yeah.
Can you like explain a little bit what work is, like what the term is, like how that's used?
Yeah. So work basically took Newton's idea of a force. So what's force? What's a force? Force is really just like the amount of effort applied to some sort of physical system, right? It's like how hard you got to push something, really, at the end of the day. The amount of effort. And it talked about how much force needed to be applied to really move something across some distance, right? So the easiest definition of work is really just a force applied to some system across some physical structure across to move it some distance. You can integrate that across your entire dynamic system for all its little pieces and parts, and you can get the amount of energy that it contains during this dynamic process. So the term energy just came to eat up all of the thermodynamic ideas, all of Newton's force-based stuff. It really just got wrapped into it because in some sense, it allowed the different physicists working in mechanics and heat and electromagnetism to all use the same concept. They could use the idea of energy and joules to represent all of these different concepts together. And so that kind of became the dominant term that won out. Okay, so back to our buddy Einstein and his super famous equation. Trying to think if I want to poke at this textbook quote again. Let's not do that just yet. Okay, so this is actually, the terms are a little bit different. So instead of mv squared, we have mc squared. C is just the term for the speed of light, right? So it is a v squared term, right? In some sense, this is very similar to Leibniz's formulation of vis viva. It's almost identical, except we're talking about the speed of light. And this equation that Einstein proposed really was trying to refer to the world of atoms themselves, right? Now, the word M is kind of pernicious in some sense, right? Because if we're following the textbook and we say that this is matter over here and this is energy over here, and they're converting into each other, then the assumption is that M, mass, is the same as matter. It's not quite a proper way of looking at things. And that makes a bit more sense when we get into the subatomic world, because we're going to start talking about particles here. And the weird thing about particles is that sometimes the particles have more mass than the things that are made out of the particles, right? And that becomes problematic. So we have to start really reconsidering what the heck this word mass means, okay? Now, if we go all the way back to so that interpretation that we're just converting between matter and energy is a little bit problematic on its face. Yeah.
I also don't know how the textbook got it so wrong when it's literally like the main thing you were taught in grade school when they say what is E equals mc squared. It's literally energy equals mass times the speed of light squared. It's always mass. I don't know how that textbook got it. How the textbook got it mixed up with matter. It's just like a word thing. Man. How did you?
Well, I think it's understandable. So here's the weird thing. Remember, guys, we still don't have a material atom. I personally hope to change that by the end of my life, but we don't. And these guys didn't have one either, right? So, and they certainly didn't have one back in Leibniz's time or back in Newton's time, right? So when they were talking about mass, they were talking about a measurable quantity. And that measurable quantity really did seem to reflect the amount of stuff that was there, right? So you have a wooden block, you put it on a scale, it weighs a certain amount. Even with Newton's formulation, if you take that block and put it on a different planet, it's going to weigh different, But all of your blocks are gonna be proportional to each other, right? So there's something intrinsic about the amount of material and the quality of the material, right? So certain atoms seem to weigh more, right? The hydrogens don't weigh that much. Some of these metals weigh a ton, right? I mean, you guys have picked up big chunks of metal. They're heavy. So it's not that crazy that people started interconverting between mass and quantity of stuff that's there. Yeah.
Well, the reason I think it's odd is I guess it's because in high school they made me take uh simple environmental science, but one of the first things when we were doing any little experiment, little bios and whatnot, was they kept making that distinction between do not, when you're measuring mass, you are not measuring the amount of you're not measuring the amount of atoms in the system. You're measuring how, because different atoms, which are technically the same unit of matter, have different units of mass.
Yeah. Yeah.
So they cannot be the same thing.
Yeah.
Matter is just the amount of atoms in a system, not was kind of how they simplified it back then. And that was
Yeah, and the quality of the atoms too, right? The atoms are different from each other, which is weird. I mean, it gets really complicated because some of these atoms are not that much different radius from each other, right? The little ones, there's some radius trends in the periodic table, but it's not like the guy down here that has 200 something atomic mass units is 200 times as wide as the guy at the top, right? It's not like that. There's something else going on with this mass concept. And like I just said, one of the quarks has more mass than the proton that's made out of 3 quarks. So what is that? What are we even talking about anymore? What is this mass stuff? It certainly can't be the amount of matter because that would be a completely logically inconsistent story to tell. And yet we can measure something at the end of the day that tells us that these pieces actually have this mass, right? So there's something else going on about mass which isn't the same as the amount of matter. Now look, there's so many different ways we can go with this at this point, but I want to go back to Aristotle's idea about activity because I think that's actually a pretty good use of the word energy here. So, another way, even if we just run with this idea that mass is in some way representative of the amount of stuff there, this equation, in some sense, is reflective of a really nice definition of energy for our purposes, which is quite simple. It's really just the amount of stuff and how fast it's moving, right? So if you think about an atom itself, a single atom with whatever mass it has, we can talk about mass here in a second, how much is that atom moving? How much is the atom moving? What is that amount of intrinsic material in motion that we have there? So energy, it's material in motion. That's what it is. Material in motion is a conserved quantity in general. You can have more material with less motion, or you can have less motion with more material, and they'll be the same. They will have the same amount of energy. So that quantity is conserved between these two different possibilities, right? There's so many different ways of thinking about that. When we were talking about the sun and how hot it was, the heat energy in the corona, right? The corona is supposed to be at 10 million degrees. That's the little flames that lick around the outside of the atmosphere of the sun. But how in the world can we send a space probe there if it's 10 million degrees? Yeah.
There's not the matter the atoms and molecules aren't close enough together to really make an effect.
Yeah, there's not that many. I mean, imagine standing. If I had a little gun that could shoot a single piece of sand at your face, right? And I shot you with like a really fast-moving piece of sand. I mean, you might not even feel it, right? But what if I had like a fire hose that just shot like a sandblaster at your face, right? That would be really bad, probably. Right?
That'd be like using sandpaper to rub your face on.
Right. So the individual atoms flying around in the corona are so few that despite the fact they're moving really, really fast, there's just not that much energy in them, right? Not that much material in motion. The motion's really high, ain't that much material. But if there's a bunch of them, then you'd really feel that thermal motion. You'd really get sandblasted, right?
By moving, you mean like vibrating, not traveling, right? Or is it both?
Well, in this case, it could be both. Yeah. So it's the sum. So temperature, in some sense, is defined as kinetic energy, which could be, yeah, it could be a vibratory motion, and it could be a translational motion as well. Yeah.
Could mass just be a measure of the like potential energy of the body?
All right. Let's talk about mass. So, in some sense, it is very much a potential. Look, where does so if we really start to think about when people first started using the word mass, what they were talking about, it actually goes back to our buddy Galileo. He was one of the first people to really do these interesting experiments. And he was doing these experiments where he would basically take these blocks and drop them and see how the mass would affect things and so forth, right? And to make it so he could actually do the timing, he put the blocks on inclined planes so they'd fall slower, right? And he started studying how mass would affect motion and so forth, and what caused it to slow down, and how friction interacted with it, and all of this. And by the time Newton comes around, Newton's really thinking about mass in terms of two basic concepts. It's basically defined by Newton, famously in his work, his magnum opus. He defines it in terms of two phenomena. What two phenomena are those? Where do we see mass show up all the time from the earliest day? I don't even expect you guys to know this. I don't know why I'm even asking, but maybe you'll think of one. Somebody mentioned it at the beginning of class. Yeah. Yeah. Gravity.
Oh,
Gravity, right? So Newton, one of Newton's main, claim to fame from his big work, the Principia, was gravity. He basically came up with the idea, although it's very half-baked at that time and still quite half-baked, of gravity, right? So there was something holding bodies to each other, right? Yeah,
Certain people have heard the story of an apple fell on his head and suddenly he knew what gravity was.
that is the
Ah,
that is the apocryphal story. Yes. Okay, so gravity. So things, presumably made out of atoms, uh, they pull on each other somehow, right? He also worked out this whole other series of things, which is quite related to momentum and eventually related to energy. And the other side of that, all of those laws could be roughly grouped together as inertial laws. What is inertia? That's a weird one. Yeah.
The speed at which something's moving through space. Or is that
Let's go more general than that. What is inertia?
I don't know
Yeah,
the term, but I know examples of what it is.
that's okay. Let's do whatever. What are you guys thinking of? You made a thing like trying to push something.
yeah.
It's like things are hard to move, right? Big heavy stuff is hard to move for some reason. Kevin, yeah.
I want to say it's how much uh I know what I want to say. I just don't know how to say it.
Yeah,
Go ahead, Dante.
that's okay.
How much energy is required to change the current direction of an object in motion? So,
Wow.
for instance, I was thinking of you have this, this little light soccer ball rolling down a hill. It's probably not going to take all that much effort to kick it up the hill. But if it's a bowling ball, it's probably going to be a lot harder, and you're probably going to break your foot.
Yeah, I think that's pretty good. I'm gonna leave energy out of this discussion for right now, until we get back to it. But yeah, it's how hard something is to move, right? So things that are actually moving already, like a freight train, they're pretty hard to slow down, right? And also when the freight train's not moving, it's pretty hard to get moving, right? The weird thing is if you take a bowling balls are hard to move, right? If they're sitting on the ground. I mean, they roll, but the weird thing is if you take a bowling ball into space, guess what? It's still hard to move. That's crazy, right? Think about that for a second. It's hard to move a bowling ball in space.
And yet there's no friction.
There's no friction. It's not sitting on anything. It's just sitting in the middle of your space station. It's hard to move still. Yeah.
Does it have to do with the density of it?
That's what we're going to try to figure out here. Yeah. Well, I'll tell you what it does have to. It does scale by the concept of mass, just like gravity scales by the concept of mass. What I mean scales by. I mean, however much mass you have changes the amount of inertia by the same amount, and it changes the amount of gravity by the same amount. Now, we'll get back to Einstein later, but Einstein famously kind of put this all together and realized that, oh my goodness, although he's famous for this, but to be honest, lots of people had kind of pointed this out by the time Einstein came along. Basically realized that gravity and inertia were two sides of the same coin. And if you took the equation for inertia and put it equal to the equation for gravity, that you could solve this whole mess and come up with a really, really precise representation of the way that bodies interacted with each other. That turned into the general theory of relativity that basically he's so famous for. Yeah.
I know that some people like pointed out like the uh like the similarities or between inertia and gravity, but Einstein was the first to have like an actual like working equation that actually worked almost flawlessly between the two and could.
Yeah, yeah. I mean, the funny thing is, so Einstein's really famous. If you talk to people on the street, he's very famous for this relativity stuff, right? But he didn't actually, first of all, almost nobody uses relativity for almost anything for any practical purposes whatsoever. Einstein actually did get a Nobel Prize, but he got it for realizing that light could produce electricity, which is super valuable for solar cells and all sorts of stuff. Nobody knows that. But yeah, Einstein kind of put these things together. He made a mathematical formula that was really, really precise in many contexts that it has been tested against in the years since, by processing this realization that inertia and gravity are kind of talking about the same thing. He famously had this thought experiment. I think this one's actually true, where he said, imagine that you are in an elevator and the elevator just, somebody cuts the cable on it, right? Well, what happens? You're falling, gravity, but it feels like you have no weight all of a sudden. Now imagine that you also just take the elevator up into space where you have no weight. It also doesn't, you can't tell the difference of whether you're falling or whether you've just been kind of removed from the inertial confines of the system that you're in. They're very, very hard to tell apart, actually. I don't know. I don't know if that's actually true or not that he had this idea, but the point is,
Planes.
what's that?
We do it. We use this idea in planes. If when a plane is in free fall, the people inside feel
Oh yeah,
they're in zero gravity.
yeah,
So this is used a lot for training,
yeah. That's true. The vomit comet, they call it.
and you
Okay.
can do it for like a minute.
Yeah, yeah, that's true. That's how they film a lot of those space movies and stuff too, from what I understand. So there's something about this lack of gravity, lack of inertia, free fall. They're very interrelated. This turns out to be true. Now the question really becomes, right? The thing that gravity and inertia have in common is this concept of mass. What the heck does it mean, right? So the concept was built before we had an atom. We still don't really have a material atom. You know, I would like to put on the table that this concept of mass can't really be understood as anything other than specifying the fact that atoms are connected to each other. And that how connected they are is what that word mass really means, right? So you're sticking to the floor, and it ain't because of fairies and magic. You're sticking to the floor because your atoms are connected to the floor. So, how connected they are is related to how many atoms you have. And not just related to how many atoms, but actually which atoms you have. Because some atoms are better at connecting than others. The bigger mass ones, yeah.
What do you mean by how connected we are? Like,
Well,
are you talking about the little hairs you were talking about?
yeah. So this is actually this is actually a figure from this book that will be out in this spring. That my wife and I have been working on for many, many years. So one nice thing about modeling the atom is actually having this kind of hairy surface. Not only is it consistent with all the mathematics that describe the atom, but one thing that's really nice is it allows us to make sense of why things that are further away are less connected, right? So when you move away from the Earth and you go up into space, right? Well, the atoms are separated from the other atoms, and that means that their physical presence is also diminished by the same, really by the same amount, which is the inverse square of the distance. This is Newton's famous formula, the inverse square of the distance. Isn't it interesting that light also disappears with the inverse square of a distance? If I take a flashlight and I run away from you, the brightness of that flashlight is also going to disappear with the inverse square of the distance. These same hypothetical structures could convey both of these phenomena. Both light and gravity could be conveyed by just imagining the atom as a physical structure that has connectivity to its surroundings. So for me, this concept of mass really just talks about how connected the atoms are to their surroundings. That's all it is. It's a scaling parameter that really scales their physical connection to their surroundings. So things start to get super weird when we get below the level of the atom, right? This is where things start to get super weird because we're told that parts of the atom have more mass than the things than the atoms themselves. Well, let's say parts of the proton have more mass than the proton itself. So how in the heck does this happen? Yeah.
Well, I had a different question.
Okay, we'll get back to that then. Yeah, go ahead.
It's a quick one. I was wondering in your model of the atom that I assume this is what is shown here. How do you have if the electron is meant like a point on the surface of the atom that's moving? How do you have like multiple electrons?
So the way that we model it, the electron is actually a motion of the surface.
Oh, so it's just different motions. Okay.
There's structures that convey the motion from the surface.
Sure.
They actually carry out the same motions as the shell surface from the chemistry books, the electron shell. So they carry out the same motions, which are very complex, actually. Okay, where was I? All right, so how in the heck? So with the subatomic world, things start to get super, super weird. All right. The problem really is, and all of this, I promise you, is leading to our discussion of how the sun does its fusion, because I want to, your textbook actually goes into the particular reactions that happen, and I think it's actually kind of fun to go through them and worthwhile. The problem is that, we're told that the atom is made out of these thingies, right? What are these thingies? They're called particles. So again, some of the particles are big, they have more mass than the things that they comprise, right? So we know something is wacky is going on here. Well, the main problem is that, what do you guys think a particle is? Maybe this is a good place to sort of like wind this down before we actually look at the particle physics of fusion. Evan.
Yeah. Particle is an itty bitty little guy.
Yeah, that's what you would think. Ethan, yeah.
It's like the second smallest little building block we had for like our atom.
Totally reasonable. Yeah, building block. I like it. What else? Yeah.
Just like a thing to measure, like a point that you measure.
Yeah, unfortunately, Dante's right. That's actually a little bit more realistic about what it means. So, this is the thing. Words matter a lot, actually. And this is in some sense, the stories that we tell matter a lot, but they also come down to these words. This is why I have spent so long talking about what the heck this word energy means, and why I'm so personally devastated by the fact that the textbook says it doesn't matter. Because words matter. And while everybody in the audience here probably thinks a particle is like a little mote of dust or a little grain of sand or something like that, that's not what physicists mean by the word particle. That's crazy, actually. So can you say what you said again? It's actually more accurate.
Point that we can measure.
Yeah, it's actually it's actually really a point where some measurement converges. Is really what a particle is in physics. So everything from the electron. What's an electron? Well, it's really complicated. Why is it complicated? Because it is actually a projection, a mathematical projection of all of the anticipated measurements that we could imagine doing using these electron measuring tools. We have a tool that measures the electron, which is really electrical tools in general. And we measure it in all these different ways, and then we bundle up all those measurements into a mathematical formula, which is hyper complex, called a wave equation, that we use to describe everything we know about that measurement system, the electrical measurement system. And we call an instantiation, one measurement or a predicted measurement, we call it an electron. Now, it's not a little ball of dust. It's literally a point, it's an index of those measurements, actually. So now you can start to see how things get a little bit wacky, because we start talking about an atom that's made out of these particles, which, you know, on first glance, it makes a lot of sense. Oh yeah, stuff's made out of building blocks, right? These aren't building blocks, though, is the problem. This is crazy, actually, if you think about it. We've gotten really comfortable with, when it's convenient, treating them like they're building blocks. But then when we really start talking, you know, well, they're not actually building blocks, you know, come on, we don't actually think that the atom's actually made out of these little, you know, structures like this kind of thing, right?
Yeah, like the amount of times I've seen artist depictions of an atom and it's just little glowing orbs moving. And I was always like, how does that make wood?
Right. So when we start talking about fusion, which sounds like that's where we'll start on Tuesday, we have to kind of go into some pretty deep rendering spaces to interpret these quantitative maps in terms of what they actually mean. Now look, maps are cool, but you have to be really careful with what you do of a map. You know, this is a map of a pre-Columbian world, which looks completely insane based on everything we know now. But guess what? It was actually pretty useful for the guys who were driving their sailing boats around the coastlines at the time. Yeah.
I want to point something out here. The water you see under Africa is entirely a guess. Because at this time, there was a huge argument on whether or not Africa ended.
Right, right.
So that's why the Spanish said, it doesn't end, we're going to go the other way. And the Portuguese were like, actually, it does end, we're going to try and sail under it.
It worked pretty good for them at the time. The maps that we have, right, these kind of maps that we have, these particle systems, they're okay. You know, we got Zoom meetings, we got TikTok, it's pretty cool. But we can do better, right? I think physics can do better. So we're gonna look at the maps. I'm out of time. I'm gonna run out of time. I don't want to keep people, but I'll hang around and talk to you for sure. The maps that we use for physics today are okay. The ones that we're going to talk about with fusion, we're going to try to give them some physical form. And then we're going to talk about how in the world the star might actually pull this off in the gaseous versus the liquid sun. Guys, I'm going to ask you at the beginning of class next time.
And I won't answer.
And the guys in the front aren't allowed to talk. So by the time we leave, we're going to say all of this again together. We're going to just say it all together. I'm going to just write a little mantra for us.
We're in the front now.
All right. I will, I'll let you guys go. Have a wonderful weekend, and we'll pick it up on Tuesday.
I just thought, you had already